that with two lines in service, the operating point is a long way from the 90-degree limit of stability. It is apparent that this connection is more able to withstand fluctuations and remain stable than the single-line connection. And for this reason, care must be taken when removing a line from service. In this example, we have generation and load at each end of the transmission circuit. At bus 1, the generation is 8,000 megawatts, while the load is 7,200 megawatts. The remaining 800 megawatts flow across the connection, that is, 400 megawatts in each line, and this supplies the load at bus 2. 2,000 megawatts are supplied from the generator at bus 2 to feed a load of 2,800 megawatts. This curve shows the situation with the two lines in service. In order to transfer the 800 megawatts across the transmission circuit, the voltage at bus 1 must be approximately 25 degrees ahead of the voltage at bus 2. If one of the lines is switched out of service for maintenance, all of the 800 megawatts will flow across a single line. In order to maintain this same load transfer, the generators feeding bus 1 must advance in phase so that the voltage at bus 1 is now about 60 degrees ahead of the voltage at bus 2. With this large angular displacement, we are already approaching the stability limit of the line. In order to avoid this, the system operator would probably reduce the load transfer before switching the line out of service. But this may not be possible due to the loading around the system. Now, in this precarious situation, any disturbance on the power system, say a loss of load or a loss of power generation, may cause the voltage at V1 to advance further, or perhaps the voltage at V2 to lag such that the load angle between them exceeds 90 degrees. Beyond this point, the load transfer across the line actually decreases, so the generators at bus 1 accelerate in an attempt to increase the load transfer. This in turn increases their angle of lead even farther, so that the power transfer continues to decrease. At this point, the generator rotors are advancing on those at bus 2. When the rotor passes the 180-degree mark, it's now approaching V2 again, so it can be considered to be lagging. It is trying to catch up to V2. But look what's happening to the power curve. Once the voltage displacement falls beyond 180 degrees, the power flow along the line reverses. Bus 2 is now feeding bus 1. The power flow in this direction is trying to assist the generator rotor at bus 1 to catch up. This is instability. The reversal of power flow in this line will probably create large disturbances on other parts of the system. Hopefully, the generators at bus 1 will pull into phase and remain in phase as they recover their original position. However, experience tells us that this is not likely to happen, and the generator will probably continue to accelerate and remain out of step with the system. This condition is known as slipping a pole and is the symptom of instability. The only remedy is to disconnect the unit from the system and then resynchronize. In the previous segment, we saw that the voltage phase displacement between the two ends of a transmission line determines the amount of load transfer that can take place. Actually, the phase angle of the voltage at the sending end bus is determined by the physical angular position of the generator rotor, which is being driven by the prime mover, say a steam turbine. As the rotor accelerates and moves ahead, so does the corresponding voltage, which is generated in the stator windings. There is actually a small angular displacement between this voltage and that of the bus due to the reactance of the generator windings themselves. Moreover, a transformer is often connected between the two, so adding more reactance. However, this is usually small in comparison with the reactance of the transmission line. When electrical load is applied to the generator, more current is drawn, consequently increasing the magnitude of current flowing through the stator windings. This current creates a flux which tends to act as a brake on the turning action of the rotor. In order to maintain the machine's speed and restore frequency, more steam must be supplied to the turbine in order to increase the mechanical output. All of the mechanical energy of the steam is transferred along the turbine shaft into the generator rotor. From here, it passes across the air gap in the form of magnetic flux into the stator, where it is converted into electrical energy. In order to maintain a constant speed, the mechanical energy input must precisely match the electrical load output. As load demand changes, the turbine governor will continuously adjust the steam input so as to produce the required mechanical input. However, as we mentioned in the last segment, this action may take several seconds to complete. The governor is far too slow to account for system disturbances. For example, in the case of an electrical fault or perhaps a load rejection, the output from the generator will fall drastically, and it will fall immediately. At this instance, then, the turbine is continuing to supply mechanical power. In this situation, the turbine's speed will begin to increase and so advance the generator rotor. This short period of time during imbalance, immediately following the disturbance and before a new steady-state condition is arrived at, is known as the dynamic period. The dynamic response during the first half second generally determines if the system will remain stable or not. You can see now why high-speed protection and removal of faults from the system is highly desirable. Let's look at a few examples. Here we see a single generating station supplying 1,500 megawatts across 3 transmission lines into a very large system. The generation on the large system is 50,000 megawatts, so the total load is 51,500 megawatts. Each of the transmission lines is carrying 500 megawatts. The power angle between the 2 buses is shown by this curve. With 3 lines in service and a total load transfer of 1,500 megawatts, the load angle here is about 30 degrees. You can see that with 3 lines in service, we could actually transfer more power. At a power angle of 90 degrees, the capacity of the transmission circuit is about 3,000 megawatts. This curve does not show speed or frequency, although it is a sine wave. It indicates the phase angle difference between the 2 voltages at each end of the line and the corresponding quantity of power which is being transferred. This vertical axis shows the megawatt output of the generator, and this is, of course, the same as the mechanical input from the turbine, ignoring the exceedingly small losses. Turbine input is considered constant for the very short time periods shown. Now, a disturbance causes one of the transmission lines to trip out. The total impedance of the transmission circuit has increased. Therefore, at this instant, the power transfer across the line decreases like this. Remember the equation for power transfer, V1 times V2 times the sine of the power angle divided by reactance. If the reactance increases, the power transfer must decrease. But this reduction in load is only momentary. Remember, the turbine is still providing 1,500 megawatts of energy to the generator. As a consequence, the rotor starts to accelerate and move ahead in phase angle. As it does this, the amount of power being transferred across the line is increased once again until it reaches 1,500 megawatts.